Okay, so welcome everybody to today's one word mathematical physics seminar. So this is a regular event hosted by IAMP, the International Association of Mathematical Physics. And if you're watching this on YouTube and if you're new to this seminar series, please click the M intersection phi logo you see down there, and then you will go to our webpage. And you will find more about this seminar series and also about the IAMP. So I hope you will join our mailing list and also to the IAMP. Okay, so today we are very happy to have Angela Capel, this is correct, and she's going to talk about rapid thermalization of the dissipative many-body dynamics of commuting Hamiltonians. So Angela, the floor is yours.
Great. So thank you very much, Hal, for the very nice introduction, and thank you very much for inviting me to give a seminar in this wonderful series of talks. I'm very happy to be here online with all of you today. And I'm going to talk about, as Hal said, I'm going to talk about rapid thermalization of dissipative many-body dynamics of commuting Hamiltonians, which is well, the talk is going to be a summary of a body of works that we have been doing in this direction for the past few years in collaboration with a few co-authors that will appear during the talk. And my idea for this talk is that I will present an overview of this field, and I will mention why these works that we have been doing have interest in several different fields. And I will conclude the talk by giving some particular examples for which examples of systems for which the results hold true. But at the beginning, I'm going to start motivating the problem and giving an introduction to the setting. And for that, let's first introduce the physics of the system in which we are working during this whole project. And essentially, the problem that we are studying here concerns open quantum many-body systems, and the motivation for the study of open quantum many-body systems is essentially that if you want to do experiments, for example, or if you want to model realistic systems, then we know that we cannot isolate systems completely, and we cannot shield them from noise, and we cannot consider them completely at zero temperature. So in particular here, what we are going to do is study the dissipative evolutions of quantum many-body systems. And for us, these systems are going to be essentially a system like the one that I'm sketching here, which is contained in an environment with which it's weakly coupled, which is something that I'm denoting by this arrow here. Of course, I will introduce all the mathematical formalism later, but I just want to give a bit of an introduction of what we are talking about here. Mathematically, essentially, what we are describing is the following. So first of all, we are considering the closed system. So we are forgetting about the environment that I was drawing here. And for the closed system, what we are doing is consider a finite system. So here, I'm not going to talk about infinite systems at all. I'm just going to consider a finite square lattice, like the one that I'm drawing here. And to each of the sides of the lattice, I'm associating a finite dimensional Hilbert space that is going to be of dimension little d. So all of them are going to have the same dimension for simplicity. The fact that this lattice is finite is going to be denoted by the two symbols that I'm writing here. And this is going to be contained in set T. So even though the picture here, it's only in set 2, in general, we're going to be considering d-dimensional spin lattices. And the idea, of course, is that now when we consider the Hilbert space associated with the whole lattice, what we are doing is considering the tensor product of all the local Hilbert spaces. So we are considering the tensor product of all these CDs that I was mentioning before for each of the sites. And the main objects that we are going to be studying here are density matrices on this system. So essentially, we're going to consider matrices that are positive semi-definite and have trace 1 that are supported in this lattice in lambda that I'm considering here. And this, of course, describes the states associated with the lattice that we're studying. But now we want to describe the physics of this lattice. And for that, we need to consider a particular observable in this lattice that is considered that is called the Hamiltonian. For us, Hamiltonians are going to be quite simple because otherwise many of the technicalities that I will present later don't hold true. So in general, what you need to keep in mind is that the Hamiltonians that we're considering are local, which means that they are sums of terms like the one that I'm writing here. So essentially, we denote this by the sum in each x of lambda of terms h sub x. So each of these terms has support in a region x. And all these regions are small enough in the sense that they are like patches, like the ones that I'm drawing here in the picture. So we are going to have a sum of patches everywhere in this lattice, like the two that I'm drawing here. Of course, they don't need to have exactly the same size for the support. But what is very important for us throughout most of the talk is that we have finite range, which means that we have k local interactions. So each of these patches doesn't have support in more than in a set that has a diameter larger than k. So it doesn't have support in too many sites, so to say. And what we are also considering is that the norms of all the terms that compose are Hamiltonian, are uniformly bounded by a certain constant that is the strength of the interaction that we denote by J. This is, of course, something that is totally trivial. The fact that this constant exists is totally trivial from the fact that this is a finite lattice and we are only considering k-local interactions. But the important further assumption that we have to make, and this is crucial, and I will mention later why, the important assumption that we have to make is that the Hamiltonian is commuting. And this essentially means that every time we consider two terms in the Hamiltonian and we consider the commutator, this vanishes. And this is, of course, trivial in the case in which you consider two supports that are totally disjoint. But when the supports overlap, like in the case that I'm drawing in the picture, this is not this doesn't usually happen. But this is a further condition that we have to impose, and I will say later why. And finally, once we have introduced the Hamiltonian, we can introduce the main object that is going to appear throughout the talk, which is going to be the Gibbs state of this Hamiltonian at a certain inverse temperature beta larger than 0 and finite. And the Gibbs state is going to be given by this expression that I write here. So it's the quotient between the exponential and the normalization factor. So again, we are only going to consider here positive temperatures, so finite betas. And this is the main object that is going to appear all the time, and it's essentially the object that encodes the physical properties of the system. So this is only to describe the closed system without any interaction with any environment. However, we are interested in how the system interacts with the environment and how the system is weakly coupled to the environment. And of course, so that the problem that appears for the modeling of the evolution of the system once it's put inside this environment, so that this problem is actually mathematically tractable, we have to make some assumptions. And I will briefly go through them in a few minutes. But I want to before highlight the consequence of this, and it's essentially going to be that the dynamics of the system is going to be described by a Lindbladian. So we will impose a bunch of conditions so that our system can be described by a Lindbladian. And a Lindbladian is going to be a super operator that I will mention in a few minutes that satisfies this condition that I'm writing here. So essentially that when you apply it to the Gibbs state, it vanishes, this quantity vanishes. And this is going to be crucial. We will see now why. But the important thing that happens, one of the important things that this Lindbladian satisfies, is that if we consider now any initial state on our lattice and we let it evolve with time, and now we let time go into infinity, then our initial state is going to be mapped after this infinite time to the thermal equilibrium, which is going to be the Gibbs state. And this is always going to happen in our systems. So we will see now why this is true, right? Just to give you a small summary. So now, why are we interested in these kind of systems? And the motivation for starting this project arose from several different fields or from several different possible applications. And I just want to highlight three of them here. One of them is that, well, we're interested in modeling noise in quantum computers, mathematically modeling noise in quantum computers, because in the end, we want to use all these results for applications related to understanding better how the performance of quantum computers does. And the nice thing is that many of these dissipative evolutions of quantum many-body systems modeled by Lindbladians can be used to model certain kinds of relevant noises that appear in quantum computers. In particular, for example, the depolarizing noise, which is something that is very, very used in experiments, is something that can be modeled in this form. So this means in particular that if we can understand these systems and we can understand how they evolve, then we can understand how to treat this kind of noise. But also something that is totally different is that, okay, we are in the first point trying to describe noises. And in principle, when we think about noise, we think that this is something bad because it's something that is going to destroy our quantum system when we want to use it as a quantum memory, for example, for a quantum computer. However, you can also change your perspective and use this in a positive way, in the sense that if you know that your system, no matter what, no matter how long you let it evolve, and no matter how you initialize it, it's always going to become very, very close to your fixed point, then if as your fixed point, if as your Gibbs state, you consider a state that is something that you want to engineer or that you want to approach for a certain reason, that means essentially that all these systems are always going to converge to this fixed point very, very fast. So this is something that is that these authors had in mind when they introduced this field of dissipative quantum state engineering, and essentially the idea was precisely what I'm saying, that if you now design a system that is based on one of these Lindbladian evolutions, then this gives you a robust way of engineering the state that is at the end of this process. Because of course, no matter how you initialize your system, you're always going to arrive there. So in principle, you can build many algorithms on this idea, and these algorithms are going to do what you want them to do in a very efficient way usually. But these two first points are quite related, but this doesn't mean that this is the only possible application that we can use for our Lindbladians and for this kind of descriptions. So one totally different application has to do with quantum phases of matters. And the idea here is that if we want to provide the definition for a relevant notion of quantum phase of matter for mixed quantum states, it's not totally clear how to do it, and there are several attempts how to do it in the literature. And one recent way to do it that has become quite well known by the community, quite appreciated by the community, has to do with the existence of rapidly mixing Lindbladians between two of these mixed states. So the idea essentially is that now you say that two mixed quantum states are in the same phase of matter if there are a rapidly mixing Lindbladian that brings one to the other, and then another rapidly mixing Lindbladian that brings the other one to the first one. So when you have these two Lindbladians, then you can say that both of these states are in the same phase, and therefore we have to understand Lindbladians to be able to classify states in this form. So this is one possible way to motivate the study of these kind of systems. And okay, once we have seen a little bit of the motivation, I have some introduction to these systems, but I have the impression that most of the people attending this talk are probably familiar with these notions, though I can imagine that some people attending this talk from YouTube maybe are not. So I will go a bit fast here, but at least I want to briefly mention this. So the idea now is that we want to describe this dissipative evolution of an open quantum many-body system. And it's kind of standard to say how you describe the evolution of a closed system, of an isolated system, because this is given by the postulates of quantum mechanics. And we know that this is given by conjugating with a unitary, and this is a map that is reversible. So it's something we can just multiply here again by u star and u, and we come back to the original state. However, our physical system that we are trying to describe now in the open context is something that is going to be, so the energy of the system is going to be dissipated with time. So we want to describe this dissipation in a reasonable way. And the way to construct the map that gives this dissipation can be, for example, by introducing a bunch of rules that we want this map to satisfy. And right now I'm talking about the description of the dissipation at a certain time. So I'm fixing the time and not talking about the evolution with time of these systems. And at a certain time, what we need for this map to satisfy is that it brings density matrices to density matrices or states to states. And of course, for that, our map automatically has to be linear, positive, and trace preserving. But we not only need that, we need something more. We are considering our system inside an environment. And of course, the map that we are defining now is something that is defined on the system, but the environment has in principle dimension that is arbitrarily large. And what we need is that when we consider the coupling of a state in our system and a state in the environment, the state in the environment has trivial evolution with under this map. So this essentially means that if we apply our map to the coupling between the state and the state of the environment, we need that this still gives you something that is positive. So that this means in particular that the tensor product of our map and identity in any possible dimension has to be a positive map, or what is the same, the map has to be completely positive. And this is a very hand-waving argument why we need that at each instant of time, our maps describing this dissipative process have to be in quantum channels. But another way to see more or less the same effect, again, also hand-waving argument, has to do with the fact that, of course, when we were considering a closed system, It was something that didn't have any environment around it. And as a closed system, we knew that the evolution was reversible. But now if we consider the system and the environment all together, something very, very large, like as a huge system, then of course, this also has, for the same reason, a reversible evolution given by unitaries, which means that now, in a very naive way, if we consider a state for the system and we tensor it with a state in the environment, the evolution of this coupling is going to be given by conjugating with unitaries. And now, of course, we trace out the effect of the environment because we're interested in what happens in the system, not with the environment. And these three maps that we are considering here, so tensorizing with another state in the environment, conjugating by unitaries, and applying a partial trace, these three maps are quantum channels, which means that now, if you consider the composition of the three maps, it's also a quantum channel. So this is another kind of hand-waving way of seeing that these maps at each instant of time have to be quantum channels. However, now we want the description of the evolution of the systems with time. And this is something that is further obtained by assuming certain conditions on the environment. In particular, we are going to assume that the environment holds no memory of what happens in the past, which is something that is usually associated to some Markovian behavior. And this is why these objects have the Markov word in their name. And apart from that, we are going to assume also that in a sense that the system doesn't affect the environment, but the environment, of course, affects the system. So at each instant of time, we are essentially tensorizing with the same state in the environment because this state is not changing at all throughout time. And when we input all these assumptions together, what we obtain is that the evolution of any initial state in our system is given by an object that is called a quantum Markov semigroup, which is a one-parameter continuous semigroup of all the maps that we were describing just before, which are quantum channels. So completely positive and trace-preserving maps. And well, this is just the definition of quantum channels, which is what I was explaining before. So this is given for this infinitesimal evolution. And now gluing all these maps together gives us the description with time. And the description with time is given by the semigroup that I was mentioning above. And the semigroup essentially satisfies these two properties that I'm writing here. So first of all, that if we consider two maps at instants t and s and we compose them, then we have the map at instant t plus s. And also that if we consider the map at the first instant of time, which is 0, then this is given by the identity. And once we have these kind of objects, the nice thing is that because of having this structure of semigroup, we know that we have an object that is called a Lindbladian, an infinitesimal generator for the semigroup, such that each map of the semigroup, so each of these maps t sub t, can be written as the exponential with time and this infinitesimal generator. So this is a very nice way of describing all these objects at once. And what we know is that this equation that I write here is satisfied, which is usually called Master's equation or Dirichlet's equation, depending on the text. And this object Lindbladian is called Lindbladian precisely because it satisfies some specific form, that is the GKLS form, where L is Lindblad. And I'm not going to go into many details of that specific form here, but I will mention some more details later. The important thing for us at this moment is that this infinitesimal generator of the quantum Markov semigroup, so this Lindbladian, satisfies a bunch of conditions that are going to make it tractable for us. So the first condition that we impose is that the Lindbladian has to be local. And this is something that is not trivial at all. So it's something that doesn't usually happen unless you impose some conditions. So in principle, you have a generator of these dynamics that can be composed of a sum of objects that have support in the whole lattice. And this could be pretty problematic for the mathematical description. So what we have to impose is that the Lindbladian is composed of a sum of terms that have support in small regions. We will see later how they work. But this is going to be crucial for the objects that will be introduced later. And then we have to further introduce a couple of conditions. And this is going to be for the study of the long-term properties of the system, of the dissipative system after a certain time. So the first condition that we have to impose is something that is called detail balance condition or reversibility. And this essentially means that if we compose now our Lindbladian L with this map, which is conjugating with sigma, sigma is going to be the fixed point of the Lindbladian. So in principle, we have a state, a density matrix, such that if we consider this map and we compose the Lindbladian with it from the left, and we consider now the dual of the Lindbladian, so the Lindbladian now in the Heisenberg picture instead of the Schrödinger picture, and compose it with the map from the right, we have equality between these two quantities. This is why this condition is called detailed balance, and it's the natural extension. It's the natural generalization to the quantum setting of the classical detailed balance condition. So if this condition is imposed, what we are ensuring is essentially that if we apply now our Lindbladian to this state sigma that we are considering to describe this relation, then this vanishes, this quantity vanishes. So this is why we have to impose it. And secondly, the second condition that we have to impose is primitivity, so that we have a primitive quantum Markov semigroup. And this is essentially telling us that our semigroup has a unique full rank invariant state, which is something that we are going to be denoting by sigma. So what we are doing now is assuming that we have a unique fixed point, and assuming that the Gibbs state, which is going to be our sigma, is a fixed point. So if you put both conditions together, essentially what you are saying is that the Gibbs state of the Hamiltonian that we were considering before is going to be the unique fixed point of the dynamics. So it's going to be the unique fixed point of the evolution. And of course, I'm saying fixed point all the time, because if you apply each of the maps of the semigroup to this sigma, it stays invariant. But this is an abuse of notation. So of course, when you apply to L, what it means is that it's in the kernel of L, not that it's a fixed point of L or something of the sort. But it's just an abuse of notation. So once we have established that we have enough conditions so that the Gibbs state is that the unique fixed point of the Lindbladian, then what we have guaranteed is the convergence to the Gibbs state always. So independently of the state on which you initialize your process, if you let your dissipative process evolve with time and you let time go to infinity, this is always going to converge to this Gibbs state, to this fixed point of the evolution. And then, since we have guaranteed convergence, the natural question is how fast is this convergence? So how fast does this happen? And there are some ways to measure this speed of convergence. Here, what we are using is something that is pretty natural. It's something that is called the mixing time of the evolution. And the mixing time of the evolution is given for any positive epsilon by the expression that I'm writing here, which is the minimum instant of time such that any evolution of any possible initial state after that time is already almost indistinguishable from the fixed point of the evolution. And this almost indistinguishability is up to an error that is given by the parameter epsilon that we are fixing from the beginning. So what this means is that now I take any possible initial state, and now I take the ball of center, the fixed point, and reduce epsilon. And then after this time t, each evolution of each initial possible state has already fallen inside this ball. So this is just a quantity to measure how our evolution behaves. And we say that we have rapid mixing in the case in which the radius of this ball scales polynomially with the system size and decays exponentially with time. And in such a case, the mixing time that I'm defining here is something that can be seen to scale polylogarithmically with the system size. And this is the regime in which we are going to be interested from now on, the regime in which we have rapid mixing. So it's something that will appear much more often during the talk. But just the important part here is the polynomial scaling with the system size. So the exponential decay with time is something that is natural to have because of the quantum Markov semigroup that is describing our evolution. And this is the key part that is not trivial at all, the polynomial scaling with the system size. And the reason why we're interested in rapid mixing is something which I want to spend some time now before moving forward to how to prove rapid mixing. But before that, what I want to mention is that here, of course, I'm presenting a collection of papers that have appeared as part of a certain project that I've been working on for a while. And the idea of this project has been that we want to prove rapid mixing of Lindbladian evolutions. So we want to prove that this convergence happens fast enough, the one that I'm writing here, and fast enough in a regime that is given by the bound that I'm establishing here. And the crucial point of this project, or the whole purpose of this project, is that inspired by the classical case, by classical spin systems, we know that well, in the classical case, you can give estimates for the mixing time, or you can give examples for rapid mixing for the whole system by analyzing only what happens in the closed system, what happens concerning correlations of the Gibbs state of the Gibbs measure in the classical case on the closed system without any interaction with any environment, and therefore without any dependence on time. And this is what we are trying to do here. So the goal of this project is to establish which kind of properties we have to assume or we have to prove on the Gibbs state of a certain Hamiltonian, which is the fixed point of this evolution, such that we can conclude something about the mixing time of the Lindbladian evolution associated with it. And this is what we will. Yes.
Yeah, can I ask a question? So you're explaining us what you mean by rapid mixing. So what happens if you don't have rapid mixing? What will this mean, this decay property? How does this decay property change?
Here, what usually happens, for example, what more frequently happens is that you have, if you have a positive spectral graph for the Lindbladian, for example, what you can show is that this upper bound is given by something that scales exponentially with the system size, and then you have the exponential decay with time. And for this, you have many, many examples, because as soon as you can prove that you have a system for which you have a spectral gap that is positive for the Lindbladian, like for example, for Davis generators associated with the toric codes or with any quantum double model in 2D, for those, you can prove an upper bound here that is exponential on the system size.
Okay.
Even though you would expect that this should be polynomial in many of these cases. So it's just what you can prove at the moment, no? But, yes. Yeah, so this is where we will arrive in a few minutes to this connection that I was saying here. And before that, let me just give a few of the implications of these results, of why we are interested in rapid mixing, before I tell you how to prove rapid mixing. And there are many, many possible implications in different subfields in quantum information and quantum computation. As I was mentioning before, there are some negative aspects and positive aspects of these kind of properties. The negative aspects mainly have to do with the fact that if you've had rapid mixing, once you initialize your system, you approach the equilibrium too fast, which means that if there was any important information in the system, in the state at which you were initializing your system, you are losing it too fast. And that means in particular that if you initialize your system, for example, in a ground state, and you approach the Gibbs state too fast, these properties that hold in the ground state but not in the Gibbs state are suppressed too fast for them to be of any reasonable use. So this would be a negative point of view in case you are modeling a noise, for example. However, if you want to see this from the positive point of view, if you are trying to engineer a Gibbs state that is at the end of your dissipative process, then if you have a short mixing time, or if you have rapid mixing, that means that your state can be constructed efficiently with a quantum device that simulates the effect of the thermal bath. And in particular, it has many implications in optimization problems, for example, if you do that via simulated annealing type algorithms. So in more specific details, the reason why we started working on this has more to do with error correction. And in a very, very blunt way, what I can say is that if we have rapid mixing, we have no error correction. In the sense that now, if you consider an error correcting code that you are putting in your Hamiltonian, to which you are associating a Lindbladian, such that this Gibbs state is the fixed point of the Lindbladian, and it's at the end of your dissipative process, and now you have rapid mixing, then that means that you have a mixing time that is of the order of logarithmic, of a logarithm with the system size, or something that is polylogarithmic with the system size. And what you expect to happen in the case in which you have a self-error correction, or if you have essentially a quantum memory, what you expect is that the mixing time of the evolution is something that should scale exponentially with the system size, so something that is much, much slower. And of course, in the case in which we have rapid mixing, this doesn't happen at all, so we cannot have self-correction, because that means that the information that we have in the initial state is destroyed too fast, so you don't have time to perform self-correction before you approach the Gibbs state too fast. However, even in the case in which you consider that your mixing time scales polynomially with the system size, you still have problems in other kinds of error corrections, because I mean, sorry, these are what you will need at least to have some other kinds of error correction, but this is not the regime in which we are, when we have rapid mixing. And this is also the regime in which topological order happens, but this is also something that is far from the rapid mixing regime. So rapid mixing regime is something that is associated with efficient implementation, and mostly that, but it's far from having any kind of error correction. And associated with that, we have some more implications and consequences that have to do with efficient preparation of topologically ordered phases of matter via dissipation. Also now, as I said, we don't have this kind of error correction, but for example, what we can do is design efficient quantum error correcting codes that are optimized for Markovian noise, which is what is described with this kind of systems. We also have stability against local perturbations, which is quite interesting. So if you have a system that is described with a Lindbladian that is rapidly mixing, and you add a local perturbation everywhere, you know that the error that you are making is not very large, because this is stable in this kind of perturbations. And more in the direction of algorithms or efficient preparation of states, for example, we have efficient preparation of Gibbs states, as I was saying, and we have efficient examples of quantum Gibbs sampling. And the very interesting thing of this and the next application that I'm going to mention, which is quantum advantage in the context of Gibbs sampling, simulation, etc., is that if you see the references that I'm mentioning here, all these references have appeared in the past year, essentially. So this is now a field that is uprising because of the results that are appearing precisely on estimating mixing times of evolutions. So this is why now many authors are using this to provide all these kind of implications in this context, using these kind of results. And finally, sorry, also the results that I was mentioning before having to do with classification of phases. If you have rapid mixing throughout the whole line of time, that means that you don't have any dissipative phase transition in this system. So this is also why you can use rapid mixing to classify this. But without spending much more time on sorry, on the implications, what I want to do now is tell you a little bit on how to prove these results. And the idea now is that if you consider the master equation that I was mentioning before, which was given by this expression here, and now if you consider the relative entropy between an evolved state after a certain time t and the fixed point of the evolution, so the thermal equilibrium to which you are converging, then it's given by this expression here. And one thing that you can do is differentiate this expression with time. And if we differentiate it with time, we obtain this expression. So where we have changed the evolution of the state rho after a certain time with this semigroup, with the composition of L and this element here. And the nice thing that we can appreciate from this expression is the following. So the relative entropy between two density matrices, that are this one and this one, is always larger than or equal to 0. And we know that it vanishes in the limit. So we know that the relative entropy is equal to 0 if and only if these two states coincide, which happens at least at the limit. So we know that this is going to be a function. So if we consider the function of this relative entropy with time, it's going to be a function that is going to be larger than or equal to 0 always, and it's going to be 0 in the limit. And what we can prove very easily, because of something that is called data processing inequality, is that this quantity is strictly non-increasing. So that means that we can maybe plot it very simply as something like this, some expression like this. And this is only to be able to see that the derivative of this quantity is something that is going to be less than or equal to 0, but it's also going to be of absolute value decreasing, which means that the behavior of minus this quantity is very similar to the behavior of this quantity. And this is giving us the grounds to define a functional inequality between these two quantities, between the relative entropy and minus the derivative of the relative entropy. So this is how you define a modified logarithmic Sobolev inequality, essentially by defining an inequality between the relative entropy of the evolved state and the equilibrium and minus its derivative with a uniform constant alpha that you can put here so that this inequality is always true for any instant of time and for any initial state rho. And when this happens, when this is true, and alpha, of course, is not 0 because you can always put a 0 here, but this is not useful at all. When alpha is not 0 and you can define this quantity, then the optimal alpha for which this is true is called the modified logarithmic Sobolev constant. And it's given by the natural quantity that you could imagine. So optimizing the quotient between the right-hand side and the left-hand side. So essentially taking the infimum over Now I'm forgetting about the time because, of course, this quantity is giving you an even better estimate when you consider any possible state rho, and of course the sigma lambda that we are fixing as the fixed point of our evolution all the time. So this is how you defined a modified logarithmic Sobolev constant, which is the optimal constant for the modified logarithmic Sobolev inequality. And now the reason why I'm introducing these MLSIs is because I want to use them to give estimates on the mixing time of the evolution. And the way to do it is the following. So if this quantity is positive, and not only that, but if this quantity in the thermodynamic limit is positive, and now what I'm saying here is essentially the following. So I was fixing a finite lattice from the beginning, but now what we can do is take a family of finite lattices such that they are increasing, they go to the infinite limit. And we can consider a family of Lindbladians associated with this family of lattices. And now we want to study this family of modified logarithmic Sobolev constants, and we want to see how they behave in the limit. And we need that the limit is positive or the limit is zero, but going to zero very, very slowly, which means that if our log Sobolev constant scales inversely with something that is polylogarithmic on the system size, this is still good enough for us. And if something of the sort happens and we apply Grunwald's lemma, we can integrate the modified logarithmic Sobolev inequality, and we can obtain the inequality that I'm writing here. This inequality is essentially giving us an exponential decay rate for the relative entropy between the evolved state and the fixed point in terms of the initial state and the fixed point. I mean, the relative entropy of these two quantities, and this exponential decay rate given by the MLSI, by the constant, sorry. And once we have this inequality, which is something that is given from the that is coming from the MLSI, if we apply Pinsker's inequality to it, we obtain the following inequality. So we know that we can upper bound the one norm of the difference between the evolved state and the fixed point by the square root of twice the relative entropy between the evolved state and the fixed point. And then by further applying this inequality here, we obtain this quantity. So we obtain that we can upper bound this by the square root of twice the relative entropy of the initial state and the fixed point, and the exponential decay with the MLSI and time. And now the important thing is that here we are considering a Gibbs state of a local Hamiltonian, which is something that we haven't used yet until now. Since we have a Gibbs state of a local Hamiltonian, we know that the worst possible value of this quantity, this always happens, the worst possible value of the relative entropy between rho and sigma is the minimal the inverse of the minimal the logarithm of the inverse of the minimal eigenvalue of sigma. So this quantity that I'm writing here. And because of having the Gibbs state of a local Hamiltonian, this is going to scale exponentially. The inverse of the minimal eigenvalue is going to scale exponentially with the system size, which means that this is going to be polynomial with the system size. So that means that now, if you remember the definition of rapid mixing, here we had an upper bound in terms of something that was polynomial on the system size, which means that if we are able to perform all these steps, then we have an example of rapid mixing. So that means essentially if we have an MLSI, then we have rapid mixing. And this is the result that we are showing here. So that means since we are trying to prove examples of rapid mixing, then it's enough for us. It's sufficient to prove examples of MLSIs, modified logarithmic Sobolev inequalities. And now let me recap what I've said until here. So we are interested in studying speed of thermalization of these dissipative evolutions. We want to provide examples of rapid mixing. And for that, we want to use modified logarithmic Sobolev inequalities. So this is what I just showed, that this implies this. And something I mentioned before is that if you have something that is the positive, that is the spectral gap of the Lindbladian. So if you have a positive spectral gap for the Lindbladian, then you get some form of slower mixing that is usually known as fast mixing or polytime mixing. And it's something in which you have an exponential scaling with the square root of the system size here, which is something that is much slower than something that is polynomial on the system size. And having a positive spectral gap for the Lindbladian is equivalent to something that is called a Poincare inequality, so satisfying a Poincare inequality in the same spirit as the MLSI. And there are examples of, well, there are counterexamples of positive spectral gaps for the Lindbladian implying rapid mixing, which means that if we want to prove rapid mixing, we really need to find a way around. So we really need to use something like modified logarithmic Sobolev inequalities. However, this is a variational problem because this is really a supremum over all initial states of this quantity, which is something that is very difficult to estimate. And the same thing happens for the MLSI. So it's still something that is very difficult to compute by hand. So what we're interested in doing now is something that I kind of hinted before is, can we find properties in the closed system that don't depend on the time, that don't involve this kind of optimization, so that only understanding these properties, we can say something about the thermalization of this dissipative evolution. And for that, we need to look at decay of correlations on the Gibbs state of the evolution, on which is the fixed point of the evolution. And now I'm going to go in not so many details from now on, because I know that time is running. And what we want to describe here in this part of the talk has to do with how correlations decay at the equilibrium of our process. So how correlations decay on the Gibbs state. And in particular, what we want to study is if you consider a Gibbs state that is, again, given by the sigma that I've been considering from the beginning, and now you study its marginal, so its reduced state in A union C, how far is that from the tensor product between the marginal in A tensor, the marginal in C? And by marginal, I just mean that you trace out the complement. So for example, the marginal in A union C would be just tracing out B from this state. And many ways of measuring this distance, so to say, have to do with different quantities that I'm going to recall here. The most canonical quantity to study correlations on Gibbs states is given by the covariance. And the covariance is essentially given by taking the expectation of an observable supported in A and an observable supported in C with our Gibbs state. And now taking the expectation of only the observable in A and only the observable in C, multiplying them, and seeing how far this is from the other quantity, and then optimizing over all possible observables supported in A and C with norm 1. So this is a quantity that is frequently used in quantum statistical mechanics to study correlations on Gibbs states. And this is a quantity that we will use here as well. However, if you can more from the quantum information community, the canonical quantity to study correlations on, well, not on Gibbs states, but on states in general, is given by the mutual information. And the mutual information is just the relative entropy between the state supported, well, the marginal of the state supported in AC and the tensor product of the marginals in A and C. So it's just this quantity here. And a third quantity that we study here is something that we call mixing condition. And the reason for calling it like this is essentially because it's the quantum analog of the classical mixing condition, considered by many authors in the classical literature. And it's essentially given by the difference that I'm writing here. So you consider the Gibbs state, the marginal in AC, and now you multiply by the tensor products of the inverses in A and C, and you see the difference from this quantity between this quantity and identity, and take the infinity norm of that. And the reason for considering these three quantities and comparing them is in particular that we can find a hierarchy between them. So we can find that the covariance, well, 1/2 of the square of the covariance, is upper bounded by the mutual information, which is in turn upper bounded by the mixing condition. And that means essentially that if we have a certain decay for the mixing condition, then we have it for the mutual information, and then we have it for the covariance. So that means that we can relate them in this form. So now if we go back to the diagram that I was showing before, we had these connections for the thermalization part, and we know that we can relate the left part and the right part in the following way. So if you have rapid mixing, you have exponential decay of the mutual information. And if you have a positive spectral gap, you have an exponential decay of the covariance. And we also know that we have the blue arrows because of the inequality that I just showed. So if you have exponential decay of the mixing condition, you have exponential decay of the mutual information and of the covariance. And in particular, you can revert the arrow here if you change a little bit the covariance and change now that you consider 2 norms instead of infinity norms for the observables. So now the natural question is, can we find a way to come to the MLSI from the right side from any of these conditions? And well, as you can imagine from the arrow here, what we are doing is relating this mixing condition, this decay of the mixing condition, to having an MLSI. And I know that I shouldn't take much longer, right? So I'm going to skip all the next parts in which I was being overly optimistic. And I'm going to conclude with the current state of the art of how this diagram is right now. So the only thing that I want to mention at this stage is that this quantity, so the exponential decay of the covariance, is among all the quantities shown here, the easiest to prove, and it's still super difficult to prove. But what you would expect is that maybe you can consider a certain Hamiltonian, and for some conditions, you can prove that this quantity holds true. And then with only knowing this, you would expect or you would hope that you can say something about MLSIs or rapid mixing or something like that. So our hope with this project is that you can say something about the rapid mixing of the Lindbladian evolution just by having some rapid decay of correlations on the Gibbs state, which is essentially given by exponential decay on the covariance. And to summarize the questions that we are actually asking ourselves here, what we have is a local commuting Hamiltonian with a Gibbs state and a local Lindbladian with unique stationary state, this Gibbs state. And the question that we're asking is, does the Lindbladian have a positive constant or polylog MLSI? And since this is going to be very difficult to ask, we really relax the question to how do correlations decay on the Gibbs state. So I will skip all the ideas on how to prove this and on which systems we can actually say something. And I will come back to this slide with a summary of the results. And the only thing that I will mention here is that the current state of the art of this problem is that if you have an MLSI inequality, you have rapid mixing. And if you have rapid mixing, you know that you have a positive spectral gap, which, as I said before, implies an exponential decay on the covariance. However, we knew from the results that I mentioned before that having an exponential decay on the mixing condition allows you to come to the mutual information and to the covariance. And what we can now say is that you can come back from the covariance to the mixing condition. So you can lift these results. And this can be done in the case in which you even have a non-commuting Hamiltonian, and even for exponentially decaying interactions. So not only for local interactions, for finite range interactions, so to say. So you can come from the covariance to the mixing condition. However, for that, you need the existence of an effective local Hamiltonian, which is something that is also pretty difficult to prove. And in principle, we can only prove it for high enough temperatures and commuting marginals, which means, in a nutshell, that you need to have a commuting Hamiltonian anyways. So this is the only way in which you can come back here. And then to go from the mixing condition to the MLSI, which is essentially what we were looking for, is something that we can do in the case in which we have a nearest neighbor interaction, so 2 local interactions, for which, well, I mean, in 1D you can do it at every positive temperature, for translation invariant systems. And you obtain a positive constant MLSI, so you obtain your rapid mixing and you're happy. And if you go to higher dimensions, you can do it also for Davis generators, which are the standard generators used to model the weak coupling between a system and a bath. And this is something that you can do for nearest neighbor interactions at high enough temperature, or for binary trees if you have a small correlation length. So this is essentially the kind of physical systems for which we can completely close the diagram that I'm showing here. And now I have a bunch of slides with some open questions and some possible directions to continue. But of course, it's something that I prefer that you ask me because I prefer that we have some discussion now and you ask me the questions that you want to ask. So I will just conclude with the last published result that we have on this direction, which is already giving you optimality of the results that you can obtain in 1D at any positive temperature and any D at high temperature. And as I said, for binary trees, you obtain the high temperature small correlation length regime. You obtain rapid mixing, but we believe that this should be improvable to only log instead of polylog. And in the case in which you only assume that you have a positive spectral gap, so in the case in which you assume that you're at this step of the diagram and you want to come to the rapid mixing, then we have something that is sublinear, which is not optimal yet. So we believe that this should be improved for sure. So with this, I will leave the possible directions to explore some open questions. And I will thank you for your attention, and I will take any questions that you have now.
Hey, thank you, Angela, for the beautiful talk. So it's time for questions and comments. Any questions? You can just unmute and ask. Daniel?
Uh, yes, so I wonder, so since you suppose that all interactions commute, you are basically in the classical setting, but with a quantum evolution. I guess that's what
Yes.
What makes it very interesting. And presumably, if you have, I mean, yeah, you commented on this very briefly, but if you have a good control on the commutators, then you can hope that everything stays true.
Yes. Yeah, I mean, there are many. I mean, it's a very good question. Of course, it's very difficult to say, no? So in the case in which you consider non-commuting Hamiltonians, there are just a few results, and none of them has to do with log Sobolev inequalities yet, unfortunately. So all of them have to do with proving a positive spectral gap for the Lindbladian. However, I would imagine that in the case in which you have something that is close enough in some meaning to being commuting, these results should survive. Because, for example, if you have rapid mixing, you have stability of rapid mixing. So in some case, I would expect to have also some kind of stability of log Sobolev inequality. And maybe this stability could be given in terms of having a small commutator, no? So you add a perturbation such that now you're perturbed Lindbladian, or you're perturbed Hamiltonian, you're only perturbed the Hamiltonian. It's not commuting anymore, but it has a small commutator, so probably something like that should survive. So this is definitely something that I think should be expected. But unfortunately, the maths are still a bit.
Because a natural
Yes.
setting would be to have diagonal interactions. I mean, something like Ising model, for instance, but with a quantum perturbation,
Yes.
small of diagonal terms, and one can hope to have a good control of pretty much everything. The evolution should be
Yes.
under control.
I totally agree. And actually, of course, well, I mean, you know this better than I. But even for the right side of the diagram, this is essentially what happens, right? I mean, even in the case of non-commuting Hamiltonians, if you add a perturbation for which you have some good estimate or some good information, then the right part of the diagram survives, because of course there's no evolution there. Once you introduce the evolution, everything gets a bit more complicated. And the main problem that we have for the MLSI is that if you are interested in improving rapid mixing, which is what we are interested in at the moment, once you add a perturbation, this kind of perturbations usually give you additive error terms. And if you need to come from an MLSI to rapid mixing with all these estimates that I presented before, it's good enough if you have a multiplicative error term that you can control, but an additive error term is pretty bad. So this is why we haven't been able to analyze additive perturbations to analyze perturbations in the past. However, in the last paper that we are having on arXiv in a few days, which is this one that I mentioned here, we realized that yes, that actually is fine if you have an additive error term that is small enough such that it is still okay. It's still something that appears here, but it still gives you a mixing time that is polylogarithmic on the system size. And this is something that I could imagine that could be used in the future to analyze this kind of perturbations that you're saying.
Thank you.
Yeah, thanks.
Yeah, any other questions? So probably this is basically the same question, but so let me confirm. So you're considering this commuting case, but is it possible that you have MLSI and this rapid decay in non-commuting case too? Is there some physics going on that you only see the MLSI for commuting or nearly commuting?
Not at all, not at all. I would definitely expect that this also happens true. This also holds true in many cases in
So
the non-commuting
this is
case.
purely technical for the moment.
It's purely technical at the moment, and the reason is actually very silly. at least for not having this kind of results from a few years ago. And it has to do with the fact that this Davis generator, which is the one that is frequently used to model these systems, when you consider a Hamiltonian that is not commuting anymore, the generator is not local. And when the generator is not local, you cannot define an I mean, you can define an MLSI, but you cannot work with it.
Okay.
And this is the problem. This is a subtlety.
You didn't say that. So yeah, in the middle, you said that the generator L is local. So that was closely related to this commuting assumption.
Yes. Yes, sorry, I should have said that more explicitly, but this is the key point. And one thing that is very interesting is that there are a couple of communities that have introduced families of Lindbladians that are pretty similar in spirit to the Davis, but they satisfy that they are not local, but they are quasi-local. Which means that now you can start analyzing all these kind of properties for these Lindbladians. And this is something that works very well for non-commuting interactions. And for these Lindbladians is for which recently some authors have proven a positive spectral gap. Which means that, okay, they are getting there, you know? So I would expect that for this kind of Lindbladians, at least in 1D, for example, for 1D translation invariant interactions, we already know that in the non-commuting case, all these properties are equivalent. And even for exponentially decaying interactions, we already know that all these properties in 1D are equivalent. And we know that when you assume the commuting case also at each positive temperature you have, every positive temperature you also have rapid mixing. So for me, this would be a natural candidate to look at, no? The 1D translation invariant at any positive temperature and really say, okay, you should probably be able to come from covariance to a positive MLSI. But yeah, still ongoing work.
Well, I was also curious about this static properties part. So
yes,
we are familiar with this covariance thing, and at high temperatures, we can. If you look at the paper by Daniel, then
yes.
we have a proof that this covariance, yeah, this is always satisfied. But what about others? Are they easy to prove in high dimensions? I still don't have any intuition about them. So you said they are equivalent in 1D.
Yeah, that's a very good question.
Yeah.
That's a super good question, and it's actually very annoying because we have some further conditions that I didn't mention here that we can prove at high enough temperature, like something that is called complete analyticity, for example, that is used for in some algorithms, and it has to do with some with some clustering condition that is defined from some conditional expectations onto the subregion. So it's really a bit convoluted only to formulate it. But we know that this condition is satisfied at high enough temperature. However, we can only prove it for commuting interactions. And the same problem is what we have when we try to show any of these conditions. So we use cluster expansions usually, or these kind of techniques. And the problem that we find is always that cluster expansions, in my opinion, behave pretty well when you have a total trace. But when you have a partial trace, like what appears here everywhere, at some point you have some problems with the counting arguments. So that means that at some point we needed to make some further simplifications, something similar to what Tomotaka Kuwahara, for example, or many other people are using recently, which has to do with the existence of an effective local Hamiltonian. And once we use this, we said, okay, we assume that we have that, and we prove that all these conditions are equivalent. So this is something that we can show. And now, when do you have this property, this effective local Hamiltonian? And we used polymer models for that, and we struggled for months, and we were only able to show that in the case in which you have a commuting marginal assumption, which means that all the marginals of all the Gibbs states have to commute, which means in particular that your Gibbs state is commuting. So yeah, we couldn't say much more than that. So I would imagine that you still have some of these equivalencies, but the assumption that we require for them to be true, I don't know if, I mean, in this former paper of Kuwahara with Kotaro Kato and Fernando Brandao, they had shown this existence of this effective local Hamiltonian, even in the non-commuting case. However, there was a flaw in the paper, and now this result is not valid. But I really hope that they can fix it, and then we have this equivalence in a more general setting.
Okay, very interesting. Thank you very much. So any other questions or comments? Okay. Okay, so if not, let's thank Angela again. Thank you very much.
Thank you very much for your attention and for inviting me to give this talk.